Hello all, my name is Erron Estrado, and I'll present to you my research on the optimization of complex geometry high-rise buildings based on wind load analysis. This formed part of a master thesis at the Delft University of Technology, together with my mentors Dr. Michaela Turin and Peter Eigener. What brought on this research was the realization of a few problems, first being of the rise in dangerous and more frequent wind events due to climate change, as well as the prevalence of complex and unique building shapes, mostly brought on due to the rise in technologies such as parametric design and BIM. But the present methods for calculating wind loads, especially for these buildings, are not very sufficient. They usually focus on regular shaped buildings and can be quite complex, and thus they are done at the late stage of design. Of these current methods, first we have the Eurocode, which usually only gives guidance for typical shapes such as rectangular and circular floor plan buildings. It is valid only up to 200 meters in height and requires the solving of many different equations and reading a lot of values from tables, which can make it quite tedious. Scale wind tunnel testing is the most accurate method. However, since it requires a wind tunnel facility and specialized technicians, it can be quite time consuming and expensive, and thus we usually test only a few options. Computational fluid dynamics is the most promising since it allows one to digitally analyze the wind flow and its effect on a building. However, it's not very widely accepted by building codes around the world, and when it is typically done now, the focus is on absolute accuracy, leading to detailed simulations which can be very computationally expensive. Thus, the aim of my research was to develop a computational method in order to optimize the shape of a complex building based on the structural effect of the wind in the early stages of design. To do this, it should be first sufficiently accurate and precise, but should be much faster than traditional methods. Also, it should be very easy to use by architects or designers or engineers, and present not only one single result, but an array of design options that one can choose from. Thus, the proposal was a fluid structure interaction-based optimization, or FSIO method. This combines four technologies, first being parametric geometry, which allows for the manipulation of a building's exterior shape based on input parameters, CFD for simulating the flow of wind and its effect on the building surface, finite element analysis, or FEA, to analyze what is that wind's effect on the structure of a building, and an optimization algorithm which can automate the process of finding better performing results. So the methodology followed these four parts. First, the method development, which was done in Rhino and Grasshopper, CFD validation and sensitivity to ascertain the accuracy and also the timeliness of the method, FSI validations to compare the results from the method with established Eurocode procedure, and the optimization test to see how much of an improvement could be made. To begin, 3 existing model buildings were chosen and remodeled within Grasshopper using publicly available data to make them parametric so that their external shape can be modified, but not too much that it deviates too far from the original architectural intent. Next was the coupling of the CFD and the FEA to form this fluid structure interaction process, where the output of the wind pressure simulated in CFD can inform the finite element analysis to get the structural performance. And the optimization will be formed based on the input variables of only geometric parameters run through the FSI method, and then the output objective would be the structural result from the finite element analysis. So this method was set up totally within Grasshopper with the geometry handled by GH components. CFD was done with Butterfly which is based on OpenFOAM, finite element analysis with Karamba, and the translation algorithm which coupled them together was custom scripted, and the optimization was handled by Opossum, which is a surrogate model-based optimization method. This was specifically chosen since it performs well with intensive simulations such as CFD. So to begin with the CFD validation, the aim of this was really to test the method's accuracy compared to physical wind tunnel tests. Thus, the CARC standard tall building model was used, for which there is already a lot of existing wind tunnel results in research. The pressure coefficient was measured at different points along the building, and three RANS turbulence models were tested, that being standard, realizable, and RNGK epsilon. The sensitivity analysis following that was in order to reduce the time taken for the simulation, since it is very important for this method. Thus, two parameters were tested, that being the number of CFD iterations and the mesh cell size. Then the FSI validation was taking the structural results of the FSI method and compare it with the Eurocode calculations. To do this, the pressures on the building were transformed into point loads and moments on the core of the building, which was modeled as a fixed upright beam for the finite element analysis. And the optimization testing uses this model, that is the Ardmore residence model, with input variables controlling only geometric parameters, that is the position of each of the wings and the angle of the corners, and the specific objective would be the mass of the concrete in the core needed to resist the deflection of the initial model. Results of the CFD validation showed that RNGK epsilon was the most promising turbulence model. We see that especially from the graph, even though the deviation was quite high, it more closely follows the wind tunnel results than the other models tested, though it took a very long time to complete the simulation. Thus, for the sensitivity analysis, first the number of iterations was reduced down to 5,000 from the initial 30,000, and we see that the time was also reduced down to a little less than 7 hours. And the pressure coefficient values were identical in each case. In the next sensitivity analysis, 5 different mesh resolutions were tested, all the way from extra fine, which took 20 hours, down to a coarse size of only 5.7 hours. And even at the coarse setting, the absolute deviation was under 20%. So it is still quite precise for an early stage method such as this. In the FSI validation results, we see two examples which are tested. The Eurocode results are in the dark blue line. This assumes a cylindrical building shape, while the gray line shows the results from the FSI method coupled with the reduction factors from the Eurocode. We see that they very closely follow each other with the exception of the highest points of the building, but this can be explained by the geometry of the buildings. So, for example, on the left, in the Nanjing Plaza model, we see at the higher points of the building where the pressure tends to be highest, there is a concave section of the facade, which leads to higher pressure. As well, on the right side, you see the absolute tower model. At the higher portions of the building, the pressure of the wind is hitting the broad side of an elliptical floor plan, thus would give higher pressure than the Eurocode assumed circular building model. You see here what the optimization algorithm is doing, where it's manipulating the geometry of the building and how that affects the force on the core of the building. After 100 iterations of this, it was able to come to an optimum which had a 24% reduction in the objective. That is a 24% reduction in the mass of concrete needed in the core in order to maintain the deflection of the original model. Much more valuable was the database of results that came out of this method, where we see the geometric results coupled with the performance of each. This allows a designer to choose between architectural aesthetics, but also the performance being the mass of structure needed. So to conclude, we see that the method was able to be implemented in Grasshopper using existing plugins as well as some custom scripting. The CFD portion showed that RNGK epsilon, along with the coarse mesh size and a low number of iterations, is precise enough but also quite timely enough for use in an early stage design process. The FSI validation showed that the results were comparable with the Eurocode results, while still being able to account for the unique geometry of each building model. And the optimization portion with the surrogate model-based algorithm gave a 24% reduction in the objective, plus gave a large array of design options to choose from. Overall, this method looks to be quite useful for an early stage design process as a complement to the more rigorous traditional methods. It enables much better performance-based design decision making in the early stages of a building project. Thank you for your attention.